Okay, so let's discuss entropy, more precisely information theoretic entropy. I start from the Shannon entropy. I think most of you know about this. We consider again a physical system with discrete states J, which runs from 1 to omega. And if you're given a probability distribution P, then we define the corresponding Shannon entropy with this. So it's simply the sum of minus P log P. Okay. And in this definition, when P equals 0, we encounter this annoying formula, 0 log 0. And this does not have a fixed definition, but in this lecture, we always understand that this 0 log 0 is 0. Okay, this is our convention. Okay, so here's the uniform distribution. So if you plug this in here, you simply find that this log 1 over omega is simply minus log omega for any j. So, and this is here you have omega and it sums to 1 anyway. This Shannon entropy becomes log of omega. Okay, and actually in general, for general P, you can show, for example, this is trivial. We see that this Shannon entropy S is non-negative, and also it's upper bounded by this log omega. So this is maximal possible value. Oh, by the way, if you look at in information theory, the Shannon entropy is usually called HP rather than S. But we are physicists, and also we are using H to denote Hamiltonian, so we use this notation here. Okay, so here is an interpretation, a standard interpretation. For each j, let ij be log of minus 1 over pj, and this is sometimes called the information content. And the interpretation is that this represents the amount of surprise when the state j is observed. For example, suppose that the probability of the state j is 1, then it means that you always get 1. And in this case, your surprise, your information content, your amount of surprise is 0. Okay? And that's true. You know that j happens, so there's no surprise at all. But suppose that this j is 1 in a million event, then this is something big, but not too big. This is like 14. But anyway, 14 is a big surprise for 1 in a million event. And in this case, this has some large value, representing a big surprise. And S is simply the average of these ij. Okay, so here you have this information content, and you are just averaging this. And one nice thing about using this is that we have additivity. So consider a system which consists of 2 subsystems, and also assume that these 2 subsystems are independent in the probabilistic sense. And so this probability for the whole system decomposes into this product. And then compute the Shannon entropy for this probability distribution. This is the definition, and you just plug this in, and then this log is decomposed into 2 sums like this. But now here you have to double sum over j and k, but you can first sum over k, and in this you usually get the marginal distribution, but in this case you precisely get this pj1, and here you get pk2, and so you get this, and you see that this is the sum of the Shannon entropies for this one and this one. Okay, this is the additivity. Here's a very simple example of the case with omega equal 2, and in this case the Shannon entropy is usually called a binary entropy, and it's this, but it's just a function of one of p's. Okay, and it's written like this, and this is derivative, choice derivative, and the graph looks like this. Okay, this is very standard and simple, and so it takes the maximum log 2 when p equal 1/2. But here our surprise is the biggest because you don't know what will happen. Here and here the surprise is 0, so the entropy is 0, because when p equal 1, you know what happens. When p equals 0, of course, you know what happens. Okay. The next quantity is called the relative entropy, also, or the Kullback-Leibler divergence. Don't ask me why it is called divergence. If you're a physicist, divergence is something like this. You know, the divergence of electric field and so on. But this has a different meaning. Don't ask me. But anyway, it's called the KL divergence, or the Kullback-Leibler divergence in information theory. And I think recently physics people also call this the KL divergence. I don't know why, but anyway, it's also called the relative entropy. And suppose that you have two probability distribution of the same system, and then the relative entropy between these two probability distributions is defined in this way. So again, it's P log P, so it's kind of entropy, but here is P, and here you have log P over Q, okay? And for one remark is that when this P, for some P, if P, for some J, if this is non-zero and if this happens to be 0, then we get infinity. So this quantity may be infinitely large, but actually this doesn't happen in our application, so you don't have to worry about this. Okay, but okay, so anyway, this is the definition. And of course, note that P and Q are not identical here. Actually, P appears twice and Q only once. Okay, so it's very different. Okay, and this is a basic property of the relative entropy, and it's non-negative. And also, this is important, it's 0 when and only when P and Q are exactly the same. Here's the proof. It's very simple. First of all, looking at this graph, you recall that for positive x, this inequality is valid. And then by taking minus of this, you see that this is valid. Of course, if you're clever enough, you can start from this, but I'm not clever enough. So I start from this and take minus, and I'm convinced that this is correct. Okay. Also note that these graphs touch only at x equal 1. So this inequality is actually a strict inequality whenever x is not 1. Okay. Now we take this definition and P log, and suppose that this is 1 over x. This is 1 over x, and use this. Then P minus this is x. Okay. And then Pj times 1 is Pj. Pj times Q over P is Q. And these sum to be 1, 1, and you get 0. Okay, good. So this proves this one. How do you prove this? Actually, note here we have inequality, but from this reason, if P and Q are not identical, this guy is not 1. So for some J, at least one J, probably at least 2. But anyway, for at least one J, this guy is not 1. Then this will be a strict inequality. So if P and Q are not equal, you can show that this is strictly larger than 0. So this has been proved. Very simple. Okay, so this is a definition. This is a basic property. If you look at this, you will find that this D may be interpreted as a distance between P and Q because it's non-negative and it's 0 only when P and Q are identical. Okay, but we have to remark that it's not a standard distance. It's an asymmetric distance because P and Q are, if you exchange P and Q, the result, the distance will be different. Okay, so in that sense, this is a weird distance. But anyway, there is something called information geometry in which you regard P and Q as a point and this as their distance, and you can develop geometry. And it's useful, and it's been used in physics a lot these days. Okay, but anyway, let's go on. So recall that this is the uniform distribution. If you look at the relative entropy between P and the uniform distribution and just compute, you get this constant and the Shannon entropy. This is actually an important observation, and you might say that the Shannon entropy is essentially the relative entropy between P and the uniform distribution. And you can even say that the relative entropy is the more essential quantity than the Shannon entropy. And if for some reason the uniform distribution plays some special role, then Shannon entropy also plays the special role. That is what I understand. But anyway, let's go on. So we have shown, we know that this is non-negative. So if you apply this to this particular case, you find that this is greater than equal to 0. So you find that the Shannon entropy in general is upper bounded by log omega. And this is something I noted in page 11. Okay, so we have given a proof. We don't use this, but because of this property, you might be interested in what this distance, the relative entropy, look like when P and Q are close. And if you do Taylor expand, you see that you find this formula. Okay, to the second order. Of course, the first order vanishes. Okay, so let's now we turn to statistical mechanics and discuss the relation between these information theoretic entropies and statistical mechanics. And this is, first of all, this is a simple observation, and actually Gibbs already knew about this. Shannon entropy and statistical mechanical entropy. So suppose that for each j we have energy Ej, we assign energy Ej, and then this is a canonical distribution. And what is the Shannon entropy of the canonical distribution? You simply plug this in here. You didn't plug this in because it's easier. And so this is the Shannon entropy for the canonical distribution. If you, okay, here you have logs, so you can rewrite this in this form. And then here you find that this Pj times Ej sum over j. So here's an average. So here you get the average of the energy. This notation is, of course, means this. Okay, this is average over the canonical distribution. And here you have log z, which is independent of j. So you can just sum over j to get 1. So you got this. Okay, so if you recall the relation between log z and the Helmholtz free energy, you can write it in this way. And since beta is 1 over t, you get this. You get this. And if you recall thermodynamics, you find that, so here's the energy expectation value, here's the Helmholtz free energy. And the difference divided by T is nothing but the thermodynamic or statistical mechanical entropy. Anyway, physical entropy for the equilibrium state. Okay, so this tells you that the Shannon entropy is equal to the statistical mechanical or the thermodynamic entropy when you consider the canonical distribution. Okay, right. And the next thing is the variational characterization of the canonical distribution. Now you take any probability distribution P and consider this relative entropy between P and the canonical distribution. And so you recall the definition P over Q. So you put the 1 over Q. And in this case, Q is a canonical distribution. So you put here, and again, you compute, you get this familiar P log P, and again, the expectation value of energy and log Z. Okay. But in this case, the expectation value is with respect to this arbitrary P, which may not be very physical. But anyway, so here you get minus of the Shannon entropy and the expectation value of energy. Okay. So we get this inequality, and this inequality is, this is equality only when P is equal to canonical distribution. Now we want to call this part beta FP. So FP is defined in this way, and then this inequality becomes this. Okay? For any P, this new FP is greater than equal to the physical Helmholtz free energy, and the equality is attained only when P is equal to the canonical distribution. So what does this mean? This means that the canonical distribution is the unique probability distribution that minimizes this quantity. Okay, you compute this quantity for many different P's and tries to make it smaller and smaller, then there is an answer. The answer is the canonical distribution, and the minimum value is precisely the Helmholtz free energy. Okay, so here we have defined a new quantity, a weird quantity. This, of course, this looks very much like the free energy, but recall that this is the energy expectation value, but this is just the Shannon entropy and nothing thermodynamic in general. But anyway, this has the form of free energy, so we call this the Helmholtz free energy for general P. And then it satisfies, it can be used to characterize the canonical distribution in a variational manner like this. And actually, again, Gibbs already knew about this. Okay, so that's all for entropy.